Welcome to this video on pathfinding. So in this first episode we're going to be taking a look at how the A-star algorithm actually works, so that once we begin programming it in the future episodes, you've got a pretty good understanding of why it works and where we're going. Alright, so here we have a grid of nodes, the white nodes representing the walkable areas in our map, and the black nodes representing the obstacles. So, of course, we're trying to find the shortest path from node A to node B, and what we need to do first is decide how far apart the nodes are. So it would be quite natural to say that the distance between two nodes is 1, and therefore by Pythagoras the distance diagonally is going to be the square root of 2, which is approximately 1.4. So quite a common practice is just to multiply those two numbers by 10, and to use the nice integer values of 10 across and vertically, and 14 for the diagonals. Alright, so I've removed the obstacles for a moment so we can see how the algorithm is going to run when there aren't any obstructions. So the algorithm begins by going to the starting node, node A over here, and looking at all of its surrounding nodes and calculating some values for each of them. So the values in the top left corner of each node are called the node's g-cost, and that is quite simply how far away that node is from the starting node. So this node in the top left corner has got a g-cost of 14, since it's just one diagonal move away from node A. In the top right corner of each node is the node's h-cost, which is basically the opposite of g-cost. It's how far away the node is from the end node. So this node is 2 diagonals far. So this node in the top left corner has got a g-cost of 14, since it's just one diagonal move away from node A. In the top right corner of each node is the node's h-cost, which is basically the opposite of g-cost. It's how far away the node is from the end node. So this node is 2 diagonal moves away from the end node, so it's got a h-cost of 28. Now the big number is the node's f-cost, and that is very simply g-cost plus h-cost. So now the algorithm is going to look at all of these nodes, and it's going to choose the one with the lowest f-cost to look at first, and that is of course this 42 in the top left corner. So it will mark this now as closed, so it will appear red, and it will then calculate all of these values again for all of its surrounding nodes. And it's quite simple to see what's happening here. These f-costs are just staying the same as it moves towards the target, because the g-costs, the movement costs, are increasing and the h-costs are decreasing, and they're just sort of balancing each other out. So it basically explores the path straight to the end. Well, no point having pathfinding in your game if you're not going to have any obstacles. So let's add those back in and run through the algorithm once more and see what happens. So once again, we look at all of the surrounding nodes and calculate their f-costs, and we'll go with this lowest f-cost of 42. And now we have a scenario where we have 3 nodes, each with an equal f-cost of 48. And so what we'll do to sort of decide which one to pick is we'll look at which one is closest to the end node. In other words, which one has the lowest h-cost. This has an h-cost of 38, this is also 38, and this one's 24, so we'll go with this one. Now, as you can see, the f-costs are increasing each time, since we're not going in a straight line towards the end. So even though the h-costs are decreasing by a little bit each time, the g-costs are increasing by even more, resulting in a more expensive path. So now the two nodes with the lowest f-cost on the map are these two 48s over here. They've got the same h-cost, so we can pretty much choose one at random. Let's go for this one over here. And now we have to look at the other one. And at this point, the most sort of promising node, as it were, is this 54 over here, and we explore that. So now we'll look at this other node with an f-cost of 54. But one thing I'd like to draw your attention to quickly is the node just to the left of it with an f-cost of 68. If we look at its g-cost, it is currently 38, but if we look how far away it is actually from node A, it's just 10, 20, 30 away. So obviously this has come on a path something like diagonally up here, 14, then across for 24, and then down diagonally to make 38. So as we explore this 54 over here, and explore all of its surrounding nodes, you'll see how this 68 updates to reflect the new best path to this node. So it now has an F cost of 60, and it is the most promising node on the map, so we'll explore that. And now we have a bunch of 62s to look at. Not much to say in the way of commentary here, just exploring all of these lowest F costs. Until now we can come back to the 68, and we explore that, and we get to explore the other 68, and now we'll observe the same effect that we saw in the first example, where we've just got a straight line to the end node, and the G costs and the H costs sort of got to balance each other out, and the F costs won't change, and we'll just go straight to the end. So hopefully you can see how this is guaranteed to find the shortest path, since as soon as you're not moving in a straight line towards the end, the F costs are going to increase, and then it will start looking at the other potential options. Let's look at one final example, and instead when we explore the little arrows, the G costs and the H costs, and I'm instead showing these little arrows which are basically indicating where these nodes have come from. So when we explore them to reflect that they sort of originated from this node, of course not worst, but in fact. Now once again, diagonal, this reflect that. So the point of these arrows, of course, is just that now that we've reached the hook to be fresh in your mind. Alright, so while that is still hopefully fresh in your mind, let us look at how this would work in terms of the actual programming. And so what I've got here is just a bit of pseudocode, meaning that it's not in any particular language, it's just basically a set of instructions. Alright, so to start off with, we create two lists. The first is called the open list, and this list is for storing all of the nodes for which we've already calculated the F cost. So in the diagrams I've been showing, all the nodes that were colored green were the ones that were currently in the open list. Then the closed list is basically the set of nodes that have already been evaluated. So those are all of the ones that I sort of ticked off as red in the diagrams once we'd looked at all of their neighbors. So once we've created those two lists, we add the starting node to the open list. So that's currently the only thing in the open list. And there's nothing, of course, at the start in the closed list. And then we enter a loop. So inside of the loop, we create a little temporary variable called our current node. And this is equal to the node in the open list with the lowest F cost. So at the beginning, that will of course be the starting node, since it's the only one in the open list. And we remove the current node from the open list, and we add it to the closed list. Then if the current node is the target node, then we can assume that we've found the path, and we can just exit out of the loop. Otherwise, we're going to go through each of the neighboring nodes of the current node, and first of all, if it's not traversable, or if it's in the closed list, then we'll just skip ahead to the next neighbor and ignore it. And if that's not the case, then we check a couple of things. So first of all, if the new path to the neighbor is shorter than the old path, so say for example that the neighbor is already in the open list, as we've seen in some of the diagrams, but then the new path is shorter, so we have to update that node to reflect that we found a better path to it. So if that is true, or if the neighbor is not already in the open list, then we set the F cost of the neighbor, which we do obviously by first calculating the G cost and the H cost, and then we set the parent of the neighbor to the current node. So that's what I was sort of trying to show visually with the arrows. We sort of keep a reference to where that node came from so that we can retrace the steps once we get to the end node. Then finally, if the neighbor is not in the open list, then we just add the neighbor to the open list, and we keep looping this, and eventually the current node is going to be equal to the target node, and the path will have been found. We'll exit out of the loop, and we'll just run a quick little method to look at all of the parents going back from the end node until we find the starting node, and that will be our path. Alright, so that's pretty much all there is to it. Of course, as we begin actually programming this in C# in the future episodes, we'll look at a couple of things a bit more in depth. But for now, that should hopefully give you a pretty good understanding of how A* works. And if you're unsure about anything, don't hesitate to leave a comment, and I'll try to help you out. Otherwise, I've also linked a couple of really good articles in the description, which you could have a look at as well. Welcome to the second part of this pathfinding series. So in the first episode, we looked at how the A* search algorithm actually works. And we saw that once we have a grid of nodes, which sort of represent the walkable and non-walkable areas of the map, then it's not too difficult to get the shortest path between any two given nodes. So what we're going to be looking at now is how we actually generate this grid of nodes. So I've got an empty scene here in Unity, and I'm quickly going to set up a simple little world. I'll make a plane and make sure it's centered at 0, 0, and maybe scale this to 3 by 3. And we'll also create a cube for an obstacle. Let's just scale this out. I'll make 2 materials, one for the ground and another wheel times. Boring. I'll copy the idea. I'm just create it. 2 script and class 2. First of all, that's going to be dealing with the good class, and the second is the class that's going to be dealing with the grid. We'll just call that grid maybe, and assign the grid class to the A* game object. Let's open up nodes. They're walkable or they're not. So let's create a public bool called walkable. And it would also be nice to know what node. And now we need some way to assign these values when we create a node. So we'll create a constructor, underscore variable, underscore walk. Our grid need a 2-dimensional
Pathfinding is such an interesting concept. There are a large variety of different algorithms that you can use and many ways to implement pathfinding in your game. Here I have used what's called breadth first search, or BFS for short, also called flood fill. You can find this style of pathfinding in games like XCOM or Phoenix Point. It can be used elsewhere, but as we will discover later, it's not optimal in many scenarios. The ground lights up in green with all of the possible locations that our pathfinder can reach from the given character's position. A small white line shows the actual calculated path that we can then take. As they move around, they also become obstacles themselves, blocking and hindering each other's movements. BFS works by exploring a node tree, starting at the root node and exploring the present depth before moving on to the next depth level. That's the technical way to describe it anyway, but it's probably easier to just show you. Here is our node tree. Each hexagon represents a node, and the starting origin node is first to be explored and added to the pathfinder. It then finds every neighbouring node to explore next. In this way, it expands out in all directions at once, exploring and adding neighbouring nodes to the list. Each node then remembers where it came from and which node came before it. This process continues until all tiles have been explored, or we have reached the maximum allowed length. When the user then hovers over a node, we can reconstruct a path by asking that node to remember the node that came before it, and trace ourselves all the way back to the origin. The best part of BFS is that it discovers every possibility. If there is a path to a location, we can know for sure that we will find it. But if you are looking for performance and want to use this as real time with lots of different navigating agents at the same time, it will be very expensive. This style of tactical turn-based movement is the perfect application for it. Let's slow down and take a snapshot of our scene. I have not named things exactly the same as I described them earlier. Instead of nodes, the ground is made up of tiles. The green highlighted part that we can actually navigate across is called the frontier. And lastly, in blue we have our characters. Turning on the debugging mode, we can visualize how every tile is pointing to the previous tile. Together they form a long chain of connected tiles, leading all the way back to our character, the root node. Tiles themselves don't really have any functions, they just store data about themselves. They are keepers of their own state. We can see the parent tile here, which is the tile we are pointing to, as well as a reference to any character currently occupying this space. You might have spotted a ladder further up the scene. We can set manual connections using the connected tile reference. More on that later. We can turn the arrows on or off using this boolean. And we also have some public properties for the Pathfinder and mouse interaction script to access our state. Our only method is to change our own color. Each color is actually a mesh. And this switch case switches between them, which perhaps isn't ideal, but it works for now as we only have two colors. The interaction script, simply called interact, uses a raycast to inspect tiles, and it can only ever hit tiles. If occupied, we call on the Pathfinder to generate new paths from this tile. Otherwise, if empty, we will attempt to navigate our selected character to that tile instead. Finally, here we have the Pathfinder itself. There is a lot to read here, so I will cut away some chaff and focus on the important bits. As soon as a character is selected, we put that character's tile in a queue with a cost of 0. The open set contains all of the tiles that we want to explore. We can read this while loop as, while there are tiles to explore in the open set, we take the next tile from the queue and add it to the frontier, and then for each neighbour, we visit those, and their cost is of course our current cost, plus 1. We add those to the open set to be explored next. When we exit this loop, that means the open set has been fully explored, or we reached the maximum length that we were allowed. But we can now highlight the frontier in green and store it for future use. We also have the make path method. Let's step through it together. This is the path we are anticipating while hovering our cursor over a tile. We do this in reverse, starting from the destination point that we are hovering over, adding each tile to a list. As long as we have not reached the origin, we keep exploring the current tile's parent until we have found our way back to the character. With all of the tiles now found, we are actually pointing the wrong way, so we reverse the list of tiles and generate something called a path from this list. The path class is really just an array of tiles that we feed to our character. Let's step out of the code for a second and view the scene again. As we press a character, we run the algorithm and find all paths. Then, as we hover over tiles, the make path method is constructing a path. Finally, as we confirm where we want to go, our character starts to move. Let's have a look at how this scene can be constructed and how you would use it if you downloaded it. We will also see how those connected tiles work. Click the drop-down window Tools Grid Generator. We can now start to generate new areas, but first we must attach a prefab to be instantiated. In the prefabs folder we have a tile game object ready for use. Drag it into the window and we can now see our options. We can set a starting position and specify the width and length of our new grid. The tool is non-destructive and we can change the settings. Hit regenerate to change the grid as we go without having to remove the old grid every time. Each tile generated this way has its own coordinates as their name, but the coordinates are not used for any purpose at the time of writing.
So we have a unit the player can control and we want to move it from one point on the map to another, preferably by the shortest path possible. We could use the built-in Unity navmesh system, but what if you want to write your own pathfinding algorithm, either because you want to have more control over it or you just want to understand how it works?
As you can see, this new grid comes with a tile generator script attached, our editor tool communicates with and manipulates this generator script. The next option is to create a ladder. Ignore the word ladder here, as I will have changed this to connect tiles before this video is out on YouTube. We can now manually connect two tiles that we would otherwise not be able to traverse between. The Pathfinder works by raycasting, and proximity is how tiles are connected normally. Without the option to manually connect two tiles, we could not create interesting areas. Our third option is to connect a character to the grid. They do this automatically at the start of the scene, but if for some reason they don't, you could make sure by manually connect them with this option. I also want to show the character move data sheet. We can create a new one as a scriptable object. Let's call this one fast character and change both the move speed as well as the maximum range that we can move. Characters in this version don't always move with the same speed. There is a duration. We only have 4 prefabs. One of those is the ladder. It comes with 2 tiles already connected to each other. We just need to line up the bottom and top tile with another grid. Read the tile generator script looks something like this. It will read the tile size directly from the mesh. So as long as you use a flat hexagonal mesh, you can read more about breadth first search on the internet. There are lots of articles and YouTube videos on the subject. Personally, I would suggest Red Blob
In this video, I'll show you how to create this nice checkerboard pattern grid, as well as highlighting on mouse over, and how to select individual tiles so you can perform your game logic.